Lecture 17 covers section 5.9. At the end of today's lecture, you should be able to analyze real and ideal machines, which constitute heat engines, refrigerators, and heat pumps using our thermodynamic temperature scale. Ideal machines are described using our thermodynamic temperature scale, and we can express the efficiency of these machines based upon our high temperature and low temperature reservoir temperatures. For instance, the efficiency of a Carnot heat engine is expressed as 1 minus TL per TH. The coefficient of performance of a Carnot refrigerator is expressed as TL per the quantity TH minus TL. And the Carnot efficiency associated with a heat pump is expressed as TH per the quantity TH minus TL. Real machines have irreversibilities, which mean their efficiencies will be less than that of an ideal machine. For instance, the efficiency of a real heat engine is 1 minus the quantity QL per QH, and this has to be less than or equal to 1 minus TL per TH. The coefficient of performance of a real refrigerator is QL per the quantity QH minus QL, and this has to be less than or equal to TL per the quantity TH minus TL. And the coefficient of performance of a real heat pump is QH per the quantity QH minus QL, which has to be less than or equal to TH per the quantity TH minus TL. Now, these equalities are all equal when the efficiency of a real machine is equal to that of a Carnot machine. That is, there are no irreversibilities associated with that device. Now let us look at these in application. Say an inventor has developed a power cycle that produces 410 kilojoules of work for an energy input of 1000 kilojoules. If the system operates between a high temperature reservoir, which has a temperature of 500 Kelvin, and a low temperature reservoir, which has a temperature of 300 Kelvin, we will want to evaluate the validity of the inventor's claim. For us to begin, we know the efficiency of a real heat engine is going to be our power output per heat input, or 410 kilojoules per 1000 kilojoules. The Carnot efficiency of a heat engine is 1 minus TL per TH, or 1 minus 300 Kelvin per 500 Kelvin. If we evaluate these two statements, we see that the real efficiency is 41%, and this is greater than the Carnot efficiency of 40%. This is an impossible power cycle. It cannot happen. Now, imagine we have a refrigerator that is cooling a cold compartment to minus 5 degrees centigrade, while our ambient air is 22 degrees centigrade. The rate of heat removed from this cold compartment is 8,000 kilojoule per hour, while our power input is 3,200 kilojoule per hour. We want to determine the coefficient performance of the real and ideal refrigerator. The real coefficient performance is our heat removed QL per our work input, W. And in a rate form, this is QL dot per W dot, which is equal to 8,000 kilojoule per hour per 3,200 kilojoule per hour. And our actual coefficient performance is 2.5. Now the Carnot coefficient of performance is TL per the quantity TH minus TL. Our Carnot coefficient performance is 9.9. Lastly, a building uses a heat pump to maintain a temperature of 22 degrees centigrade, while the ambient or outside temperature is 10 degrees centigrade. The heat delivered by the heat pump is 500 megajoules per day. We want to determine our minimum theoretical work required for this heat pump to operate. We recall that our coefficient performance for a heat pump is our heat supplied per our work input, or in rate form, QH dot per W dot. And this has to be less than or equal to the Carnot coefficient of performance of a heat pump, which is TH per the quantity TH minus TL. Or if we re-express this in terms for our work input, W dot has to be greater than or equal to QH dot times the quantity TH minus TL per TH. Substituting in our values, our W dot has to be greater than or equal to 500 megajoules times 1 minus 283 per 295, which is equal to 20.3 megajoules.